Worlds exist where iron may fall as rain at night. This isn't science fiction, but a phenomenon astronomers are observing on exoplanets, challenging everything we thought we knew about planetary weather. It makes you wonder if our understanding of planets has been far too Earth-centric all along.
That's precisely it, Oliver. For centuries, our definition of a planet was shaped by the few examples in our own solar system. But with thousands of exoplanets now confirmed, the universe has revealed an astonishing diversity that stretches the imagination and our scientific models to their limits. These distant worlds aren't just variations on a theme, they're entirely new compositions.
And the Iron Rain is a perfect starting point for that. It sounds like something from a fantasy novel. What exactly is happening on a world like WASP 76b to create such an extreme meteorological event?
WASP 76b is a tidally locked planet, meaning one side perpetually faces its star, while the other is in eternal darkness. The day side is incredibly hot, reaching temperatures high enough to vaporize iron. Powerful winds then sweep that iron vapor across the planet towards the cooler night side. As it reaches the darkness, the temperature drops dramatically, allowing the iron to condense and fall as molten droplets. It's a truly infernal cycle, driven by that constant contrast between the day and night sides.
So the rain isn't just unpleasant, it's literally molten metal. And this concept of extreme heat isn't limited to just iron. You're saying some planets get so hot that basic elements like magnesium can drift through the atmosphere like ghostly gases?
Exactly. On these worlds, often called ultra-hot Jupiters, the heat isn't just fierce, it's transformational. Temperatures climb high enough to rip apart molecules. Iron, magnesium, even rocky material can evaporate, becoming part of the atmosphere. A typical mountain range, if it existed, would simply soften, flow, and eventually become part of the air. These planets are essentially natural laboratories, showing us chemistry under conditions our solar system simply can't replicate.
That's an incredible thought, a planet where the very ground could be part of the sky. But it's not just the temperature that's surprising. What about worlds like 55 Cancri E, where you suggest there might be oceans of lava?
55 Cancri A is a rocky world, but it orbits so incredibly close to its star that its surface may be covered in a vast ocean of molten rock. Imagine a horizon not of water, but of liquid stone, glowing orange and red. This planet is also likely tidally locked, with one side receiving intense stellar heating. We've even found signs of an atmosphere rich in gases released from its hot interior, suggesting it's geologically active, not just a dead cinder. It's a living furnace, constantly reshaping itself.
And on the opposite end of the spectrum from blazing lava, you have worlds that are so dark they reflect almost no starlight. TREES-2b, for example, is described as darker than coal. What makes a planet so incredibly black?
TREES-2b is a gas giant that reflects less than 1% of the light that hits it, making it the darkest known exoplanet. It actually emits a faint red glow from its own heat, but it doesn't shine back at space in any familiar way. Scientists believe its atmosphere contains light-absorbing chemicals, possibly vaporized sodium, potassium, or gaseous titanium oxide, which prevent light from scattering back. It's a contradiction, a burning hot planet that appears black. It forces us to redefine what we mean by dark.
So planets aren't just about extreme temperatures and bizarre compositions. Many defy our expectations about orbital mechanics and their interaction with their stars. For centuries, the idea of a double sunset was purely fictional, but now we know some planets orbit two suns. How does a planet even form in such a complex gravitational environment?
It's one of the great surprises. Kepler-16b, for example, truly circles two stars at once. For a long time, models suggested planet formation would be very difficult in binary systems, where two stars are constantly tugging at surrounding material. But these discoveries show that nature is far more creative. Worlds can still emerge and hold stable orbits, even with two sources of light shaping their days and seasons. It's a solar system built around a partnership.
And then there are planets that don't orbit any star at all, rogue planets drifting alone through the galaxy. These sound like incredibly bleak, dead worlds. Is there any possibility of warmth or even conditions for life on such a body?
At first glance, yes, they seem hopelessly dead. But that might not be entirely true. A thick atmosphere on a rogue planet could act as an insulating blanket, trapping leftover internal heat from its formation or heat generated by radioactive decay in its core. Deep below the surface, conditions might remain warmer than expected. So a planet doesn't always need a sunrise to remain a world. Some can carry their own hidden story through the dark, potentially even harboring liquid water beneath an icy crust if enough internal heat is retained.
That's a remarkable thought, a kind of self-sustaining warmth. Speaking of orbits, some planets zip around their stars so quickly that their entire year passes in less than an Earth day. What does time even mean on such a world?
It collapses our familiar scales. These planets cling so tightly to their stars that gravity keeps them in relentless motion. An entire year could pass in just a few Earth hours. The star would loom huge in the sky, and heat would be overwhelming. Tidal forces might even lock one hemisphere into constant daylight. The phrase "next year" loses all meaning. Time itself feels completely different when a planet races through its orbit faster than Earth spins through one ordinary day.
And some planets are so close to their stars they're literally being stretched out of shape, like WASP 12b, which you say looks more like an egg than a sphere. Is it just misshapen, or is there something more dramatic happening?
It's far more dramatic. WASP 12b is so close to its star that colossal tidal forces are pulling it into an egg-like shape. But more than that, the same gravitational strain is actively stripping material from the planet, drawing gas away towards the star, slowly tearing the world apart. So it's not just misshapen, it's a planet under visible stress, being distorted and consumed by the very star it orbits. It's a tragic, temporary place, caught in the act of losing itself.
A planet essentially being devoured by its star. We think of planets as these stable, permanent objects. This changes that perception entirely. Then there are planets that orbit the remnants of dead stars, like pulsars or white dwarfs. This seems to defy logic, as the star's death should have destroyed anything nearby.
It was a huge shock to astronomers. When stars die, especially massive ones, they swell into red giants or explode as supernovas. Either event should sterilize or consume nearby planets. Yet some planets are still there, orbiting white dwarfs and pulsars. They either survived impossible odds, clinging on as the star violently transformed, or they formed later from the debris left behind. Both scenarios are remarkable, showing planetary birth can happen even in the ashes of stellar death.
It sounds like a cosmic second chance, and some of these stellar remnants can even forge planets from their own destroyed material. I've heard the term diamond world associated with planets around pulsars. Is that literal?
The planet around pulsar PSR J1711, 1438 is a dense world, thought to be the carbon-rich remnant of a once larger companion star, stripped down to its core. If that's correct, under the extreme pressure and heat, that carbon could be in crystalline forms. So while Diamond World might be an oversimplification, it highlights an astonishing truth. A world might exist that wasn't gently assembled from dust, but carved out of the death of a star, possibly packed with extreme crystalline carbon. Planets can arise from ruin, not just birth.
From diamond worlds to planets made of essentially nothing, superpuffs are wider than Jupiter but have the density of candy floss. How can something so enormous be so light?
These are truly bizarre. Superpuffs like Kepler-51b are enormous in size, sometimes wider than Jupiter, yet astonishingly low in mass. If you could find an ocean big enough, they might actually float. They're wrapped in vast, incredibly diffuse envelopes of hydrogen and helium that extend far from their tiny cores. Their outer gravity is so weak that the atmosphere simply balloons outward, giving them this ghost-like bulk. They challenge our formation models because they look so fragile and temporary, more like celestial mirages than solid worlds.
It defies intuition, a planet that's mostly atmosphere. Then there's the concept of tidally locked worlds, where one face is in permanent day and the other in permanent night. What would the climate be like on such a planet?
On these worlds, the star-facing side can be hot enough to melt rock, while the far side plunges into temperatures cold enough to freeze gases from the air. The extreme temperature difference would drive violent supersonic winds trying to redistribute the heat. However, between those extremes lies a terminator zone, a narrow twilight belt where conditions might be more moderate. Here, dawn and dusk never end, and this band could potentially be the most stable region for habitability, creating a permanent temperate band around the planet's middle.
So light becomes geography, not a cycle of day and night. But even more unsettling is the idea that the very atmosphere could be made of stone, skies filled with vaporized rock. That feels like something straight out of a nightmare.
On the hottest rocky exoplanets, yes, the atmosphere isn't primarily water vapor or nitrogen, but rather rock itself. When a world orbits close enough to its star, the surface rock heats until it melts and then begins to evaporate, creating an atmosphere of mineral vapor with elements like sodium, silicon monoxide, and other gases released from molten ground. The sky isn't above the landscape, it's rising from it, exhaled by the planet's own glowing crust. In some cases, this vapor could even condense and fall back as droplets or grains of rock rain.
That's a complete inversion of how we perceive land and sky. And some planets are so affected by their star that they're losing their atmospheres like comets. Gliese 436b, for instance, is trailing hydrogen. Is this a common fate for planets that are too close to their stars?
It can be. These worlds are intensely heated and blasted by radiation, causing gas to stream away into space, forming long, comet-like tails. It's a haunting image, because a comet's tail is natural, but a planet with one feels tragic and unstable. Gliese 436b is shrinking over immense stretches of time as its star strips away layer after layer. This process, though invisible to the eye, shows us that a planet can be eroded by light itself. It makes every orbit feel less like a path and more like a slow surrender.
It's almost as if the star is actively dismantling the planet. This brings us to another atmospheric oddity, clouds. On Earth, they're made of water, but you're suggesting alien worlds could have clouds made of sand or glass?
Absolutely. On much hotter planets, the raw materials for clouds are utterly different. Some exoplanets may form clouds from silicate particles, the same broad family of materials that make sand, rock, and glass here. High in the atmosphere, where temperatures and pressure find the right balance, these substances can condense into fine mineral grains and drift like alien weather systems. Imagine looking up and seeing clouds composed of tiny specks of rock, perhaps even glowing or scattering starlight in unusual colors. A cloud, after all, is defined by suspension, not just by softness.
So even powdered stone can float. It makes you reconsider the very definition of a cloud. And what about planets where there's no solid ground at all? Just a descent into deeper and deeper atmosphere.
Many gas giants and ice giants we discover offer no true surface in the earthly sense. If you were to fall through their visible clouds, you wouldn't strike a solid plane. Instead, pressure and temperature would rise relentlessly, hydrogen might shift into exotic states, and chemistry would grow stranger with depth. The idea of down would survive, but the idea of a floor would not. These are worlds without shorelines, without stone underfoot, without a place to stand. A planet doesn't have to be solid to be real. Sometimes it's just a deep atmosphere all the way into mystery.
That's a fascinating redefinition of a world. And then there are those that are incredibly old, like the planet around PSR B162026, nicknamed Methuselah. 12 billion years old, existing before our sun was born. How does such an ancient world challenge our understanding of planetary formation?
It expands our timeline dramatically. Methuselah suggests that worlds began appearing very early in cosmic history, when heavy elements were much rarer and the Milky Way itself was still quite young. It tells us that planet formation is a robust process that's been happening for almost as long as the universe has existed. Our own solar system, by comparison, feels quite young and wonderfully recent.
It makes you feel like a newcomer in a very ancient universe. And some young worlds glow from their own leftover heat, like embers of creation. What does that tell us about their formation?
It tells us that planetary birth is a violent, energetic process. These young, massive worlds still carry enough leftover heat from their formation, from gas collapsing inward, material crashing together, gravity squeezing the interior, to glow brightly in the infrared. They're essentially still cooling down from the violence of becoming. For astronomers, these glowing infants are incredibly valuable, offering a rare chance to study early planetary evolution as it's still happening, revealing the atmosphere, age, and mass in ways reflected starlight never could.
So we're seeing their birth trauma in a way. And then we have planets that are carbon-rich, suggesting that some worlds could have crusts made from minerals rare on Earth. Could these actually be diamond planets again, but in a different context?
In a way, if a planet forms in a region where carbon is especially abundant compared to oxygen, it builds from a very different chemical foundation. Instead of our silicate-heavy geology, such a planet might have far more carbon-based materials throughout its crust and mantle. Under immense pressure, that carbon could indeed be squeezed into crystalline structures like graphite or even diamond, not necessarily forming glittering surfaces, but influencing the entire internal geology. A rocky planet doesn't have to mean Earth-like. Nature can use entirely different ingredients to build a world.
It forces us to rethink what rocky even means. Speaking of different elements, some planets are thought to have hidden cores wrapped in vast mantles of exotic ice. What kind of ice are we talking about here?
Not the brittle, cold ice we know. Deep inside certain planets, under immense pressure, water can lock into exotic crystal forms that don't exist naturally on Earth's surface. So a planet might have a central rock core, then layers of compressed, often hot, high-pressure ice, then lighter material above. These superionic or ice 7 phases of water are distinct from liquid or solid ice we're familiar with. This means a planet's interior architecture can be vastly different, challenging our assumptions about what a water world can contain.
A kingdom of crushed, alien ice. It sounds like something straight out of Jules Verne. And yet another concept that stretches my imagination is planets that orbit so far from their stars they feel almost detached, pushing the limits of our formation models.
These far-flung giants challenge how planets are supposed to form. Classical models suggest that building massive planets far out in a disk is difficult due to sparse material and slow growth. Yet nature has clearly done it. This opens up bigger questions. Did they form where we see them now, perhaps through a different process more akin to the birth of a small star? Or did they form closer in and then get scattered outward through gravitational encounters? Either answer implies a much more dramatic history than a simple, calm disk would suggest.
So even the way a planet forms can be a story of upheaval. What about planets whose skies are permanently hidden beneath steam? That feels less like a planet and more like a pressure cooker.
That's an apt description. Some planets may be so hot and water-rich that their skies never fully clear. Instead of blue air above a sea, they're wrapped in thick, dense layers of steam. Water exists, but not in a gentle way. Surface temperatures are high enough to keep oceans violently evaporating, feeding a dense envelope that blocks any direct view of the sky. These steam worlds take one of the most hopeful ingredients for life, water, and push it into a far more intimidating, even lethal state.
It makes you question what habitable really means. We often define the habitable zone as where liquid water could exist, but that's clearly an oversimplification. Some planets might be in that zone, yet remain deeply hostile.
Precisely. The habitable zone is a starting point, not a promise. A world can sit in that zone and still be utterly hostile. If the atmosphere is too thick, it overheats in a runaway greenhouse. If the star flares violently, radiation hammers the surface and strips away air. If it's tidally locked, one side roasts while the other freezes, unless the atmosphere redistributes heat effectively. Habitable conditions depend on a delicate balance of planetary details, clouds, tides, atmospheric composition, not just distance from the star. A seemingly gentle ocean world from afar could be lethal up close, hundreds of miles deep with extreme pressures and an acidic atmosphere.
It's a reminder that beauty from a distance can conceal profound hostility. But for all these wild, strange worlds, The most surprising thing is arguably how we even find them. Most aren't directly photographed, are they?
No, most are found indirectly. The transit method, where we detect a tiny dip in a star's light as a planet passes in front of it, is very effective for finding large planets close to their stars. Then there's the radial velocity method, where we detect the subtle wobble of a star as a planet's gravity tugs on it, giving us clues about its mass. And we can also infer planets from gravitational microlensing, where a planet warps the light of a background star for a brief moment. These methods are ingenious. A planet announces itself not by shining, but by subtly altering light or motion around it.
So a planet too faint to see still makes its star dance. It's remarkable how much we can learn from these indirect clues. And you're suggesting that for all the astonishing worlds already known, we're still just scratching the surface.
Absolutely. Our detection methods have biases. We're best at finding large planets close to stars or systems aligned just right. This means the catalog of 6,000 plus exoplanets isn't the full truth of planetary diversity. It's a first draft shaped by what our current technology can most easily see. Somewhere beyond that bias, in the vastness of the galaxy, there are undoubtedly worlds even stranger than the ones that have already shocked us. The universe consistently outgrows our imagination. The weirdest planets may still be waiting in the dark, ready to overturn our picture one more time.
Daniel, this conversation has been a truly mind-bending journey. It's clear that our solar system is just one tiny example of planetary architecture, and the universe is far more inventive than we ever gave it credit for. We've explored worlds with metal rain, lava oceans, and skies made of rock vapor, along with planets that defy the very concept of day and night. Thank you for helping us understand these extraordinary astronomical discoveries.
My pleasure, Oliver. It's a field that constantly reminds us of the universe's boundless creativity.
If this discussion about the universe's most bizarre planets sparked your curiosity, consider sharing it with someone who also loves to contemplate the cosmos.